Hello! Today we are going to talk about laser. Let's begin by reviewing the nature of light as we did in the previous videos. And what I did then is I went out 2.5 million light years to the Andromeda Galaxy, which I am representing with a little dot and a couple of spiral arms out there. And somewhere in that galaxy is a hydrogen atom. And the electron in a hydrogen atom can have 5 or more energy states in it. So the Rutherford Bohr model of the atom says that a hydrogen atom has a nucleus consisting of 1 proton. I'll make that as a positive charge. With an electron in the Rutherford Bohr model, the electron is orbiting the nucleus. That's not really what's going on, but it's a good model to explain how atoms work. And according to the Rutherford Bohr model, especially the Niels Bohr additions to it, this can have multiple energy levels, and they are represented by the electron being in higher or lower orbits. And like I said, the electron in the hydrogen atom can have 5 or more. I'm not sure exactly how many, but at least 5 different energy levels. Let's say that this particular hydrogen atom has an electron at the 3rd energy level, and as happens, they will spontaneously lose that energy, dropping down to some lower level. And let's say this one drops down from the 3rd level to the 2nd level. So drop down its energy. And of course, what happens when an electron drops from one energy level to another? It creates a photon. So that energy was lost to the universe as a photon, which we discussed is a wave through space-time itself, whatever that is. It seems like when light was first discovered to be a wave, we had to have something for it to propagate through, so we invented the luminiferous ether. Later we discovered we don't need no stinking ether for the wave to move through, and now we have something called space-time, or the fabric of space-time, which now the current theories are that it might be some kind of an electric field, whatever. Nevertheless, there's something, either nothing or something, that this wave of light that we call a photon is going to expand through, and this expands with a radius expanding at the speed of light in a vacuum. And the other thing we discussed about the nature of this photon is as it expands, it might encounter other atoms, and those atoms will have electrons around them, and it may or may not interact with one of those electrons. If it does interact with an electron, that electron is going to be kicked to a higher energy state, and that photon completely disappears. So we have this photon that is expanding away from its origin in the Andromeda Galaxy there, and let's say it reaches my eyeball on Earth or a photodiode or who knows what, and there's an infinitesimally small chance that this photon is going to react with any particular electron, but there are so many electrons that it's going to encounter that there's a good chance it's going to interact with one of them. And let's say it interacts with an electron and some photoreceptor in my eye, kicks it up to a higher energy level, that entire photon is completely gone. So we have this photon that's 5 million light years across, and suddenly it's gone. And that's what we discussed in the previous video. And instead now all that energy has been put into an electron in a photoreceptor in my eye, causing that photoreceptor to trigger a nerve, and eventually my brain sees that as a photon of light. One question that came up is that, well, could this react with an electron over here and an electron over there, 5 million light years away? And the answer is no. There is exactly enough energy to interact with one electron and kick it into a particular energy state. And what happens after that depends on what's available at the point of that electron. But it cannot interact with more than one electron. It's either going to interact and it's gone, or it's not going to interact and it's still there. And so that's the wave nature of the light. And we talked about the particle nature and said that that's probably an illusion, because we know something originated here and then it did something here, and that happened in a straight line at a certain amount of time, and we say, that must have been a particle. So particles, like even electrons, are actually waves, and have this same nature. So we're talking about quantum physics here, and this is my best understanding about how it's thought of today. But remember, this is quantum physics according to Bob, and it is subject to change as I correct my understanding of these theories, or the theories might change themselves. So there we go. There's that photon. It interacts with an electron. But let's see what things can happen when that photon interacts with an electron. So let's clear this out. So we had our photon started out over here and eventually interacted with an electron over here. And two or three things can happen. One, it can kick that electron up into a higher energy state. So let's look at our atom. There's a nucleus of an atom with an electron, which might be one of many electrons around that atom. Kicks it up into a higher energy state, but the higher energy state it kicks it up to is not stable, so it just simply drops back down. And so what happens then? All of that energy that it absorbed is going to be re-emitted as a new photon originating at this point here. So, and that's going to happen immediately. And so basically all we've done is move the wave. Remember we talked about that being a wave of quantum probabilities. We just moved the origin of it and started everything all over again. So that's one thing that can happen, and we discussed that is what happens in glass. So we have some glass and some air, and here comes a photon, and it interacts with an electron, let's say right there. That electron absorbs the energy, drops it immediately, and then a new wave begins there. And the nature of Fresnel reflections and refraction happens because of this re-emission of the electron. Notice that the wave of that photon is once again expanding, and if we have a whole bunch of them, of course we'll have lots and lots of photons making new waves, which means we end up with two new wave fronts going in two opposite directions, which is a Fresnel reflection. And if this comes in at that glass at an angle, so here's our glass, and here comes our wave in at an angle, it's going to react in sequence. So it's going to react with this electron, then that one, then that one, then that one. And of course, what I mean is that this wave has many, many photons in it. And so the many photons are reacting with electrons in sequence. And so this one makes a wave that gets so big. This one's a little later, so it gets less big. And so what eventually happens, this is difficult to draw immediately, but I'll just try to draw some smaller and smaller waves there. And notice we get a wave front that angles off that way. So the wave came in this way and then angled off that way, and that's the nature of a Fresnel reflection off axis. And then what happens inside here is there is a delay caused by the interaction of waves inside the glass that causes an interference wave that goes through a little slower, and the basic result is that these don't get as big as fast, and so the wave front is at a different angle in the glass than outside the glass. And that's a little bit of a tangent here from what I'm talking about, but that's what we talked about, what happens when a photon interacts with an electron in glass, usually. So it absorbs it, immediately releases it, and it spreads out from there. What's another thing that can happen? Let's say, for example, this encounters another hydrogen atom, and there's an electron that happens to be in the second energy state, and this photon hits it. Well, this photon was created by an electron in a hydrogen atom going from the third state to the second state. Now it's encountering an electron that's in the second state, and it may go right past and not interact with it, because we know that with any particular electron, it's a very small chance of interacting. But let's say it does interact with this one. It's going to kick all of that energy back into it, and it's going to kick it up to that level of the second energy state, which is stable in the hydrogen atom. And so actually it's the third state there, because the first state is lower. So it went from the second state to the third state because, once again, this photon had the energy of an electron dropping from the third state to the second state, creates this wave of light of a particular wavelength. I picked that particular number because I know a little bit about it. I forgot the exact wavelength. It's somewhere in the 600 nanometers. It's kind of a bright red, and it's known as hydrogen alpha. So when a electron in a hydrogen atom drops from the third state to the second state, it creates a photon with a wavelength that's called hydrogen alpha. It's in the red part of the spectrum. If electrons drop from other states to other states, we get different colors, but we'll worry about that a little later. So once again, we have this electron dropping from the third state to the second state, creating this photon of hydrogen alpha light. It encounters this hydrogen atom, whose electron happens to be in the second state, absorbs that energy and kicks it up to the third state. So went from the third state to the second state here. It had exactly enough energy to kick it from the second state back to the third state, which is stable, and it stays there. So this time it absorbed the energy and it just stayed up in that third state. But as what happens, eventually that's going to decay and it's going to drop down to the second state and re-emit another photon of hydrogen alpha light. So that's the second thing that can happen. So one thing, an electron can absorb the light, and if it doesn't go to a stable state, it immediately drops it and creates a new photon of the same wavelength. Or it can hit an electron that's just in the right energy state that kicks it to another stable energy state, such as this hydrogen alpha light, kicking that electron up into from the second state to the third state, and it stays there until it eventually decays and re-emits. What's the difference? If it doesn't kick it to a stable state, it's re-emitted immediately, and we have such things as Fresnel reflections or other types of reflections or refraction or whatever. But if it kicks it to a stable state, it doesn't release it immediately at some other time. And so we get a completely different phenomenon. When this happens up in interstellar space, it happens very frequently in gas clouds, which contain a lot of hydrogen. And when they absorb that energy, they re-emit it randomly. And so we get a glow in that hydrogen gas cloud, and we get these glowing clouds out there. There's a picture of them. There's tons of them all around the whole universe because there's lots of hydrogen, lots of light from stars energizing this hydrogen, and the most common color of light that comes from these is hydrogen alpha, which gives them the red color. Another thing you can see with this hydrogen alpha is if you have a filter that blocks everything but hydrogen alpha and put that on a small telescope and point that at the sun, you're not going to see the white light sun like this. You're going to see what the sun looks like if you only see the hydrogen alpha light that's being created at the sun. What's the sun? It's a big ball of hydrogen. And there's a lot of hydrogen ions in the atmosphere of the sun. So if we filter out everything but the hydrogen alpha light, here's what the sun looks like, and we can see these solar prominences and such that make the sun look rather spectacular. So when you see these pictures of the sun with all these details and the prominences around it and such, that's usually taken with a hydrogen alpha filter on the telescope. So we get this hydrogen emission. Once again, it's random. So it absorbs it, emits it randomly, and it is what it is. Now another thing that can happen, let's go back to our glass. That energy is absorbed and released immediately, and we get these new photons expanding out from wherever that light hit the glass, and what happens is what I've described before. But what if this is not transparent like glass? Let's say it's something that's opaque, not metallic that's reflective, but something like, I don't know, wood, plastic, tar, who knows what, anything that might not be reflective. It's going to absorb that energy, and the difference between something that's transparent and something that's not, the transparent substance like glass immediately releases that energy and it goes through and does what it does. So if something is transparent, that's going to release that energy right away and the light's going to go right through. Now, opaque objects will absorb that energy into a higher energy state, and what tends to happen is that that energy is radiated as blackbody radiation. And so the energy is dropped and makes photons at random wavelengths that can be all the way from radio through infrared, through visible light, on through ultraviolet, and we get what's called blackbody radiation. But some things will hold on to that energy and then drop it at a specific different wavelength. So let's say we have something that's kind of semi-transparent but has some material that's phosphorescent in there, such as phosphorus. It kicks those electrons into a higher energy state, and then it drops them, and it goes from a particular state to another particular state. I don't know which ones and what the atoms are doing in phosphorus or other phosphorescent materials, but it emits that at a different wavelength. So we can have something that we energize with ultraviolet light, and then it glows for a while because it holds onto that energy. Those electrons go into a higher energy state, randomly drop them, going from the higher energy state to a particular lower energy state, which emits a particular wavelength of light, or maybe a range of light, because it might be, for example, things that are phosphorescent tend to have light that's dominated in the green, but there's a lot of other colors there too. And so we get something that's phosphorescent that releases that light a little later. So those are things that can happen. Now, one last possibility I want to talk about is, what if we have a hydrogen atom here, and here is an electron up in the third energy state, n equals 3. There's our electron up in that high energy state, and here comes our photon. And it interacts with that electron. What's it going to do? Well, I'm going to get a little closer look here. Remember, our photon is several fields of electricity. And positive, negative, negative, positive, positive, negative, negative, positive, etc. And this is going to be the strongest one. This one's a little weaker. And this is the weakest, and there might be more. And if we draw a graph of that, we've got something that looks like this, or maybe even goes out and, in fact, theoretically, it eventually just peters out. And so there's our strongest part of our photon, and keeps changing polarity and eventually gets weaker. So this comes by us in space. We see these multiple fields go by, not just one pulse of energy. So when that photon hits this electron, it doesn't just kick it up and let go, it's going to vibrate it. And if it vibrates it just right, it might get caught in a higher energy state. But we've already got this at the third energy state here, the same state that the original electron was in. And here comes our hydrogen alpha light, which has just the right amount of energy to kick that from state 2 to state 3, but it's already in state 3. So what's going to happen? This is going to go up and down in energy as that photon passes it, and it's going to kick it down at the peak to the lower energy state. And I'm not fully sure of what's going to happen here, because it may go back up to the state. I don't know if this is part of the theory or not, but it certainly is likely to get stuck back at the lower state. So when this absorbed the energy and dropped it again, it's going up and down, absorbing, dropping, absorbing, dropping. It's going to act just like any other electron that absorbs a photon, then drops it. It's going to create a new wave. So there it goes. But it's also dropping from one energy state to another. So it's creating another photon. So it absorbs the photon energy, releases it, creating a new photon, dropping from this energy state down to the next lower energy state, and put a little far there, and creates yet another photon. I'm going to put them right on top of each other. So we had a situation where our electron was in a high energy state, and when that photon came by that could have put it up to that state, actually pops it down to the next lower state and causes it to emit a photon. And of course, we had the interaction between this and the electron, so that's going to absorb and release the energy as an identical photon. And then when it drops down, it's going to create another identical photon. Why is it identical? Because it's the same energy state that the original electron went from and to create the first photon. So we end up with that photon creating another identical photon, plus the normal interaction leaves essentially the original photon intact, just starting from a new place. This can actually get quite complicated. I don't want to get into the Fresnel-Huygens theory about how this is going on all through space and stuff. Let's keep it simple here. So this photon that was created by an electron going from state 3 to state 2 in a hydrogen atom comes down here and encounters an electron in state 3, pops it down to state 2, causing another photon to be created, in addition to itself essentially just continuing on. So what do we have? We now have two photons, basically, if I understand it right, superimposed on each other. So we have double the energy. We've increased the energy of that photon. We have two of them actually right there on top of each other. They might not be completely superimposed, but they're dang close to each other. So what was that? Well, let's go back to the original. When that electron dropped the energy and created the photon, it emitted a photon, and that's called spontaneous emission. It happens randomly. But here, when that photon hit the electron in the higher energy state, it stimulated it to emit a photon. So we had stimulated emission. So originally spontaneous emission, then stimulated emission. And that's part of what the name of laser is. I'll just write that up here. S-E, stimulated emission. In fact, it's electromagnetic radiation, so we'll put an R up here for radiation. Stimulated emission of radiation. We're getting close to the word laser now. So that happens all the time. A lot of the light that hits you is from stimulated radiation. I have fluorescent lights lighting me right now, and some of the light hitting me is the same exact thing. These photons are being created. They hit other electrons in the high energy state, knock them down to a low energy state, and create stimulated emissions. So I have a lot of spontaneous emission hitting me and a lot of stimulated emission hitting me. No big deal. It's what this kind of light is. And the same thing as light from the sun. A lot of the light from the sun is stimulated emission. Light from those emission nebula, some of it's spontaneous emission, sometimes it's stimulated emission. So no big deal. But let's try to manipulate this a little bit. So what we're going to do is create a tube of hydrogen. Now, I don't think that lasers can be made with pure hydrogen. At least if they are, it might take more energy than is worth or whatever. But just to simplify the idea, we'll pretend that we can make a laser with pure hydrogen and talk about complications later. So I have a tube that's got a little bit of hydrogen in there at very low pressure, a couple of electrodes. I put a high voltage in between here. So nice high voltage. And I'm going to get that gas excited and knock a bunch of those electrons into a high energy state. So what I have now is a bunch of electrons in high energy state, and what that's going to do is they're going to randomly drop down to low energy states and emit light, and I'm going to see that tube light up. And I'm going to see all different colors, well, not all different colors, but I'll see a lot of hydrogen alpha that will probably dominate it. It depends on certain things, I believe, but we'll see hydrogen alpha, so that red light. But there's also hydrogen beta, and there's, I forgot what the third one, there's like 5 different or 6 different colors that can come from hydrogen. So we have the hydrogen alpha, which is red, then we have other colors at the far end of the spectrum around blue and violet and such. There's the spectrum right there. I don't remember off the top of my head, but there's the spectrum coming from hydrogen right there. The bright red line to the right is the hydrogen alpha, then we have the other colors. But we're only going to be concerned with the hydrogen alpha at this point. I'm not going to explain it any deeper than that at the moment. So all this light is coming off, nice red light. And we have inside here a lot of electrons that are in their high energy state. That's not the way it usually is. Normally the electrons will be in a lower state, not as many will be in higher state. But now we have a huge number of electrons in the high energy state, so we have what's called a population inversion. So that's one of the first things we need for laser to work. We need a lot of electrons in that high energy state for this to work. So now this light is being created, so what's happening? A lot of those photons are hitting other electrons in a high energy state, and what's it doing to them? It's knocking them back down to a low energy state and causing them to emit photons. So we have a lot of these, I don't know if you want to call them double photons or what, but a lot of photons that are basically right on top of each other. And so we have, if we look at the waves going through there, we have a lot of waves of photons going through that are just right in sync with each other because they were created together. And so we have these stimulated emission photons traveling through this medium. And I guess any photons that happen to go in a straight line are going to escape going this direction, and there'll be more stimulated emission going in these directions than the other directions, but I don't know if that's really important. But we have stimulated emission going everywhere. So we're going to get a little extra light going this way rather than that way. I don't know how much extra, but a little extra. But now what we're going to do is just get our stuff out of the way here. put some more inverted population over here. I'm going to put a mirror on this end. So it's got some glass with a metal coating, and just for this discussion right now, we'll just assume it's a 100% reflective aluminum coating, whatever. It's not necessarily the case in working lasers, but we're just trying to get the basic idea right now. So this emission, which is going in every direction, some of that light is going to hit this mirror, and if it hits it at an angle, it's just going to go out. But if it hits the mirror straight on, what's it going to do? It's going to go straight back through. So we have a lot of light, both spontaneous and stimulated emission, going every which way, but some of that is going straight down toward this mirror. And those wave fronts going through here are going to hit that mirror and reflect back and go back through the medium. So what's going to happen? Well, we have these wave fronts going through, causing more stimulated emission, getting stronger and stronger and stronger, hits that mirror, turns around, goes back through the same way, stronger and stronger and stronger. So we're going to get a stronger wave going back this way through the mirror. So we have an increasing strength going this way. Now it's going to get even stronger going that way. And so we're going to have a wave front coming out of here that should be measurably stronger than light going any other direction, because not only do we have these wave fronts going this way, causing more and more stimulated emission, but we also have that light that tried to go this way hitting the mirror and going back and causing even more stimulated emission. And so, could we have a laser at this point? I've never heard of a laser being made this way, but maybe it's enough. But anyway, what's happened? We have amplified our light by manipulating the stimulated emission, and we have a stronger light beam coming out this way than around the rest of the tube. So we have light amplification by stimulated emission of radiation. But classically, your laser is going to improve on this by putting another mirror at this end. Now, what's going to happen if we just have 100% reflection? So 100% reflection, 100% reflection. Well, the light's just going to go back and forth and create more and more energy. And to tell you the truth, I don't know what's going to happen. I suppose if we're pumping enough energy in there, we can damage something. We could either burn up the mirrors, which would cause it to stop working, or we might actually damage this tube. Who knows? It might even explode if we get enough energy in there. But I think most often what's going to happen is that energy is going to create a lot of heat. Those photons are going to be absorbed by the glass or whatever to the point where it's just going to be dissipated as long as we're only putting a certain amount of energy in there. But if we put a lot in there, I think we could do some damage. But that's not what we're trying to do anyway, because we're going to take one of these mirrors and we're going to make it somewhat less reflective than the other one. How much? I don't know off the top of my head what to expect. But let's just say this is 90% reflective. So 100% reflective, 90% reflective. So what's going to happen is 1 out of 10 photons that hit this mirror are going to escape. So we're going to have a beam that's basically 1/10 of the energy that's going back and forth is going to come out of here as a beam of light. And that beam of light is going to have some very useful characteristics. One, it's going to be either a single wavelength, or it's going to be maybe multiple wavelengths of light, but like the hydrogen spectrum here, it's going to be, let's say this is hydrogen, we're going to have hydrogen alpha, we're going to have hydrogen beta, certain discrete wavelengths. And what we could do is manipulate these mirrors, the reflectiveness, to not work on the wavelengths we don't want. So we just easily eliminate those. So we end up with just a single wavelength of, in this case, hydrogen alpha light of around 600 some odd nanometers coming out of this device. And so we have pretty much one wavelength. It's not perfect, but it's very near. It's got a very, very high Q. In other words, unlike maybe a regular LED or maybe the tube itself, which has a spectrum that's kind of like centered on that 600 some odd nanometers, but spreads out a lot, this laser is going to be much more centered on that particular wavelength. So very pure light of a pure wavelength. That's number one. Second thing is this is going to be collimated. Now I believe the collimation is a bigger function of the length and diameter of the tube than anything else, because if any of this light that's going at the slightest angle is going to eventually work its way out. but only light that is going straight at this and very near to it. So light that goes this way might escape and disperse a little bit. Light going this way might escape and disperse a little bit. So there's going to be a little bit of dispersion, but the longer this is, the narrower this beam will be. So your classical tube gas lasers like this, or other lasers I'll talk about that use thin rods of material, are going to be fairly well collimated. LED lasers typically are not very well collimated and need a lens to collimate the light. So that, I think, adds credence to my belief that the collimation is largely a function of the length and diameter of the tube. Another thing is that the light is coherent. All these waves are together. All these electric fields are traveling together. Plus, minus, plus, minus, plus, minus, plus, minus. So all of these electric fields of the light are coming out, and they're perfectly spaced all together. So that's coherent. Now, one thing I don't quite understand is, why is it coherent? Because these atoms are randomly distributed through this light, perhaps evenly, but they're going to be much closer together than a wavelength of light. So it seems like I would have all different phases in here. So that's not going to make it coherent. I've heard it said that the coherency is caused by this being a resonant chamber. Yeah, I don't believe that, because that means that we would have to have that length of the laser tube or the rod or whatever the laser is made of very close to an exact multiple of the wavelengths of light. And so let's just say this is 1,000 nanometer infrared light. I would have to have that accurate to in the order of 10 nanometers, maybe even 1 nanometer accuracy in the length. And even if I could do that, heat expansion is going to foil it and make it something other than a perfect multiple of wavelengths. So what makes this coherent, I think, is a different mechanism. It very well might be just that one coherency just is a little higher than the others and tends to dominate, and by the end of it we end up with all of our waves going together in here. So I'm not exactly sure what mechanism causes the light to be coherent. It might just be that one phase dominates and gets amplified more and more and more, and there you go. If there's another way, I'm open to learning about that. But anyway, the light comes out coherent. All of our wave fronts are lined up perfectly with each other. So those are the three characteristics of lasers that make them very useful. The light is collimated, the light is coherent, and it's very pure in color. Now, the uses of lasers take into effect those properties, but also we use lasers for cutting. So we can get a lot of power out of laser, and even get megawatts out of lasers. Kilowatt lasers are not that uncommon, used for cutting metal and such. Your little laser pointers, you know, here we have a, there we go. Oh, wrong one. This is an ultraviolet laser. Hard to see that one, isn't it? Here we go. Green laser. Okay, so that's going to be half of a milliwatt. What's the rating on this? It's going to be, let's see, 532 nanometers. There's got to be a output power. What's the power on this thing? Less than 5 milliwatts, it says. So their laser pointers should be less than 5 milliwatts, but there's no guarantee. You go buy these things on eBay, they might be a lot more powerful, so be careful with them. Talk about these in just a minute. So they can be made very powerful, so we can use them for cutting. They're used in surgery for both cutting and cauterizing. There's all sorts of uses for lasers. They're used for optics, using their qualities of being collimated and coherent. All sorts of uses for them I'm not going to get into, but once we've got the laser invented, we can make low power lasers for optical stuff, high power lasers for industrial stuff or medicine. That's the basic idea of how a laser works. Now, I used hydrogen as my example here. I cannot find any literature of anybody making a pure hydrogen laser. It probably could be done, but there are going to be problems with it. So if we go to gas lasers, two that come to my mind that are the most common, and by far the most common, is helium neon. And here's a helium neon laser tube, and just a quick drawing of it. We have a mirror on this end and a mirror on that end, and our tube got our electrodes here, and I'm not going to draw them exactly, but inside is a little, what they call a capillary tube. And this is filled with a mixture of mostly neon with a little helium. And basically it's a neon laser. So the light it produces is going to be a light particular to neon. Just as an aside, all the different elements and their different electron energy states, when an electron moves from one state to another, it produces wavelengths particular to that particular atom and that particular pair of energy states. And that's how we can see across vast distances what elements are in a star or a galaxy or whatever, is because we can see what colors of light are coming from it. And we know this particular wavelength of light only comes from a particular element. So this is going to make light that's particular to neon. And the reason the helium is in there is because the neon by itself takes more energy to get into that population inversion, but we throw a little bit of helium in there, and the helium atoms collide with the neon atoms, kicking the electrons into higher energy states with less energy input. So that's why we have the helium neon laser. So we have the helium to help kick those electrons in the neon atoms into the high energy states to create the population inversion. And then we have the laser action taking place inside this capillary tube. Notice it's a little short of the end, but that doesn't matter. We have the mirrors at the end. And these mirrors are designed to emphasize a particular wavelength of this neon, the one that has the most energy, and to block the other wavelengths, so we only get one wavelength of light out. Now, one thing you'll see about a helium neon laser is that it has light going in both directions. So we don't have a 100% mirror on one end, and I think that might have something to do with the manipulating of the light, so we only get a particular color. I'm assuming that these two mirrors are a little different and work in concert to get the color and the power that we want out of that helium neon laser. Another type of gas laser I'm familiar with is argon, which produces a bluish light, several wavelengths of bluish light. So once again, you have to manipulate it or filter it. I saw a demonstration once where the argon laser went through a prism, or was it a diffraction grating, doesn't matter, and it split off into several colors of different colors of blue light. And so to get the one color, we'd have to have either filters or otherwise manipulate the process to get only the one particular color. And of course, CO2 makes lasers too. That does laser in infrared light. And by the way, the first helium neon lasers only produced infrared light somewhere at 1500 nanometers or something like that. And it took a while to manipulate them to produce a good beam of visible light. And then they became very inexpensive and are still in use everywhere because of their low expense. I used to have a Laserdisc player, an early Pioneer Laserdisc player, which had a helium neon laser in it. There's a problem with that. Helium cannot be contained. The molecules are so small that they will escape any vessel you put them in. And so the helium slowly works its way out of this tube, and eventually there's not enough helium to kick the neon electrons into their higher states, and the tube will quit working. So one day I turned on my Laserdisc player, and instead of it starting up, it just started making a little ka-tink, ka-tink, ka-tink sound. So I wondered what was going on. I opened it up, and I could see the laser tube ka-tink, flashing, ka-tink, trying to start, wouldn't start up. That was the end of that. But all Laserdisc players and CD players and everything, they haven't made Laserdiscs for a while, but your Blu-ray players all use diode lasers today. Okay, so now we've talked about that, let's talk about some other types of lasers. Another type which was developed early and is still made are crystal lasers. The earliest ones I think were made with ruby. So you take a ruby rod, cut the ends perfectly parallel, polish them, and put the proper mirror coatings on there. And the ruby is going to have some impurities in it. I don't remember what they are off the top of my head. It seems like it's the iron impurities, but don't quote me on it. And that's the actual lasing material in there. So the ruby laser is going to be surrounded by a flash tube. Let's see if I can draw a flash tube here. Use my skills of an artist to try to make a drawing. Let's see if I can do it here. Okay, Does that look like a flash tube to you? Yeah, it goes around it. Could be xenon. They use krypton, I think, gets more power, but they will flash that tube, and that excites the impurities in the ruby, sends them up into a population inversion, and of course we get the spontaneous emission, which then causes stimulated emission, and then goes back and forth between the mirrors, and we get a beam of light out of the ruby laser. It's just a pulse, so it's not steady. These were made before we had the gas lasers, which can give us a steady beam. These just give a pulse beam. I don't know what color it gives, but I do know that one way we make these types of lasers are with ruby. Here's a diagram of how one's made. Another type is with a material called neodymium doped YAG, or YAG is yttrium aluminum garnet. So the yttrium aluminum garnet makes a crystal, and it has yttrium in there as impurities. Not really important, but just what I think I remember. And that is the different type of material that can be used to make a laser. So we have ruby, neodymium YAG, and I'm sure other types of crystals have been used to make lasers like this too. And then of course we have what everybody has everywhere now, and those are diode lasers. Well, maybe not everybody, because the compact disc is going by the wayside, and so is Blu-ray and all those. But we can also make lasers with LEDs by simply shaping it properly. So we have our layers of material here. I'm not going to try to make a perfect drawing. There's a drawing there. But we have our layers of gallium and arsenic, or gallium arsenide, or whatever we're doing. And one layer is going to be the layer that makes the light. And it's cleaved. They cut these such that we get these nice parallel pre-polished surfaces, and this can produce a laser light. I have not read that they put a metal coating on there or not. The Fresnel reflections might be enough, but I don't know. But anyway, we can get laser where this is actually a light emitting diode that we're getting the stimulated emission from. So that can be done, and so we get this laser light coming out of the diode. Another type is called a vertical cavity surface emitting laser, which instead of the laser coming out of the side of the layers are made, I don't know the exact composition, but the light comes out that way instead of from the side. There's a diagram of what they call a VCSEL, vertical cavity, VCSEL, vertical cavity surface emitting laser. And so they're used everywhere also. So anything that can cause emission can be made into a laser if it's manipulated correctly. So there's the basics of how a laser works. Just a quick finish up here. I've already shown you my green laser, and that doesn't look as good on camera as it does on the board. I have a spot that's, I would say, is about 4, not quite 4 millimeters in diameter, but you see a bigger spot in the camera because laser, the light just acts differently. I see little speckles in the light which are typical of laser beams. So if you suspect something might be laser, look at it, and if there's little speckles in the light, they don't move around. It's not like they're scintillating, but you see little specks. That's the interference pattern that is typical to lasers, and this has that, and it never picks up on camera. But, well, it's got a nice little spot there. I've got a spot that's less than 3 millimeters in diameter right there, so this is dispersing a fair amount. But it doesn't look as good on camera. But the interesting thing about these green lasers is that they don't use a simple laser diode. They have a multi-stage process to get the green light. They do have green diodes now. I don't know if they're making pointers with them, but this pointer goes through a 3-stage process. So let's take a look at that. Starts out with an infrared laser. And the wavelength is 808 nanometers. And it's a fairly powerful laser, more powerful than the final output of the pointer. And that goes to a crystal that is a neodymium doped YAG. We talked about that earlier when we talked about solid lasers. So we have our neodymium doped YAG. So yttrium aluminum garnet with a little bit of neodymium in there, when the neodymium is the element that gets excited to create the laser. So we are using this 808 nanometer laser to pump a neodymium YAG laser, and that's going to give us a wavelength of 1064 nanometers. So it's again infrared, much deeper in the infrared than the original laser. And so that laser goes through a crystal, which is a potassium titanium phosphate. It's actually potassium titanyl phosphate. So it's a mixture of potassium, titanium, and phosphorus. And that has an interesting effect as the light propagates through here, basically like any other kind of a transparent medium, except we get that interference pattern that slows it down. In this case, it also causes double reflections of some sort that causes the wavelengths to become half the distance apart. So we have a wavelength going in of 1064 nanometers that bounces around in there, and what comes out, let's show our 1064 nanometers, what comes out is half that wavelength of 532 nanometers, which is our green light from the laser. And this comes out at about, well, for a laser pointer, less than 5 milliwatts, hopefully. You can get more powerful ones, but you really shouldn't. This comes out at a lower power of less than 5 milliwatts. So I don't know what the power of this is. I can't find any really good numbers for a 5 milliwatt laser, but it's going to be more than 5 milliwatts. I just don't know how much more. If I find the number, I'll stick it down there in the editing. So here comes our final beam of 532 nanometers. I'm not quite sure why the next stage is needed, but I'll throw it in there because I know it's there. Goes through a double concave lens that's going to expand the beam. And then it goes through another lens, a double concave, according to the drawings I've seen, that's going to recollimate the beam. Remember that collimation makes our wavefronts all flat, or our rays perpendicular to that and parallel. And so that's what this final lens does. And the last stage is an infrared filter to block this far infrared here, because that's going to be a fairly powerful beam that we don't want getting to our eye. I have heard that a lot of laser pointers don't have that filter, which means that they're putting out a lot of infrared light. You can probably find videos on YouTube of people using those and focusing them on balloons and popping the balloons because there's that much power coming out, but there should not be more than about 5 milliwatts or less coming out of your laser pointer. So that's how a green laser pointer is made, at least when I got mine. There might be laser pointers now that use diodes only, because they do have diodes that can make green light these days. I also have my ultraviolet laser, not really ultraviolet, but pretty close. Now, I doubt very much you can see anything. I can see about a 2 millimeter wide bluish white spot. It's very faint. And I suspect this has a lot of light other than the violet, because it looks like a heavy bluish cast on a white beam. So I think there's more colors coming out of here than the near ultraviolet that is listed on the pointer, which is 405 nanometers. But I can show it to you because I'll just take my notes here and shine it on the board. You probably can't see anything. Now you can. That looks like about 3 millimeters wide, about 2.5, 3 millimeters wide. Probably looks bigger on the camera. But notice it's bright blue. That's because this paper has chemicals called optical brighteners in there that absorb high energy light such as UV and near UV and fluoresce in the blue range. And so that does not do that. So I just see a very faint. When I first bought this, I put a battery in it and I turned it on and the beam was almost invisible. I said, oh, that's bad battery. Put another battery in, same thing. And I thought, well, that sucks. I got a bad laser. Its beam is almost, well, you can't see that on the camera, I'm sure. Then I pointed it at something that had some optical brighteners in it. Whammo! So, yeah, it's not very visible because it's very close to the edge of visibility of the spectrum, 405 nanometers. 400 nanometers is officially the edge of the visible spectrum. Of course, we can see a little beyond that, just like we can see a little bit into the infrared. So this doesn't look like much until it hits something with optical brighteners. I don't have anything that's phosphorescent handy, but you shoot this at something that's phosphorescent, something, a glow-in-the-dark substance, and it really energizes it quite a bit. Anyway, those are your laser pointers. A little bit about safety. Of course, laser light can be very powerful. I talked about using laser for industrial purposes, and so you can burn things with them. You can cut metal with it. You can weld with it, I think. But they can also use these lasers in medical procedures such as cutting or cauterizing. They can even use lasers for eye surgery. So lasers, because of their purity of the beam and the collimation that they can control and the power that you can get into it, can do all kinds of jobs. And you're probably not going to usually encounter these high power lasers unless you're in one of the fields that uses them, and you will be trained properly to use the precautions you need to use to work with those kinds of lasers. And you'll see people using laser goggles when they're working with dangerous lasers. When it comes to laser pointers, theoretically, they should be less than 5 milliwatts, but don't count on it. You can get more powerful laser pointers. But assuming that it's less than 5 milliwatts, these are Class 3 lasers. Now they've changed the classification. They used to be called Class 3A. Now they're called Class 3 something else. But basically, if it's Class 3 or lower, it's safe to handle as long as you're not an idiot. Now, like a Class 1 laser, I think the warning is don't stare into the beam. Class 3 lasers and whatever class they show them now, the warning is do not look at the beam at all. But theoretically, if the power is 5 milliwatts or less, your blink reflex will be fast enough that the laser will not have time to do any damage. So it takes time to do damage, and at less than 5 milliwatts, you will close your eyes instinctively before the laser can do damage. Now, of course, if you hold your eye open and point your laser into it, that's going to be a different story. Now, astronomers like to use these green lasers as pointers, because a red laser, if you go out at night and point a red laser, you're not going to see it because the red light doesn't scatter enough for us to be able to see. I suppose if you put enough power into it, you could see it, but at 5 milliwatts, you cannot see a red laser beam. But you go out at night with a green one, it scatters much more, because the redder it is, the less it scatters, the bluer it is, the more it scatters, and you can actually see these beams very brightly at night. And amateur astronomers like to use these as pointers to show people, oh, look at this, look at that, and the other thing. And some even mount them in their telescopes to align their telescopes with what they want to look at. Instead of a spotter scope, which is rather difficult to use, they'll simply mount a laser pointer there. But most amateur astronomy organizations have banned the use of laser pointers because they are a nuisance. People are out there trying to take pictures, and someone else is out there with a laser pointer crossing their field of view that they're trying to take a picture of, ruining their picture. And also, people have dark adapted eyes, and if someone accidentally points it towards you, it's going to blind you temporarily. I mean, really badly. It won't be permanent, but it sure be annoying for a moment. So they are usually banned at amateur astronomy events, except certain places where people are taking non-astronomers and showing them stuff. So I use them all the time to show things because I can point at something and you can see what I'm pointing at. But be advised, in the United States, it is a felony to point one of these at an occupied aircraft. And in fact, that goes for any really bright light. If you shine a light that could temporarily blind the pilots, it is a felony. So do not go pointing this at aircraft. It'll get you in big, big trouble if you're caught. And they take it very seriously. The people have been jailed for pointing these at aircraft. Don't do it. But just generally, don't be pointing it at people at all, because even though theoretically you will blink before it does any damage, you don't want to be pointing this in people's eyes. So that's about all I have to say about laser in this introduction. So if you found this useful and informative, please give me a thumbs up down below. Hit that like button. It really helps the channel and helps other people find these videos when they're looking for this kind of video. And if you'd like to help me put these videos online and keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. Oh, look, a QR code. And if you want to make a one-time donation, you can go to paypal.me/Voced, VOCED. And if you'd like to learn electronics technology for free, you can take my free course at Vocademy.net. So a big thank you to my patrons at Patreon and other donors. I couldn't do this without your support. And thanks to everyone for watching.